So what are the definitions? Can I begin with a fact, a highly important fact that I didn't call directly attention to earlier? Suppose I have a matrix and I look at AX equals 0. Suppose the matrix has a lot of columns so that n is bigger than m. So I'm looking at m equations, a small number of equations, m, and more unknowns. I have more unknowns than equations. Let me write that down. More unknowns than equations. More unknown x's than equations. Then the conclusion is that there's something in the null space of A, other than just the zero vector. The conclusion is there are some non-zero x's such that AX is 0. There are some special solutions, and why? We know why. I mean, it sort of like seems like a reasonable thing, more unknowns than equations. Then it seems reasonable that we can solve them. But we have a clear algorithm which starts with a system and does elimination, gets the thing into an echelon form with some pivots and pivot columns, and possibly some free columns that don't have pivots. And the point is here there will be some free columns. The reason is there will be free variables, at least one. That's the reason that we now have this a complete algorithm, a complete systematic way to say, okay, we take the system AX equals 0, we row reduce, we identify the free variables, and since there are n variables, and at most m pivots, there will be some free variables, at least one, at least n minus m, in fact, left over. And those variables I can assign non-zero values to. I don't have to set those to 0. I can take them to be 1 or whatever I like, and then I can solve for the pivot variables. So then it gives me a solution to AX equals 0, and it's a solution that isn't all zeros. So that's a important point that we'll use now in this lecture.